was looking at ultimately 3 new syntheses. The only one that I would expect could potentially show up on the ACS test would be, my guess is that last one. I would expect to see kind of that reductive amination at some form or another. It doesn't have to be the reduction aspect of it, but at very least you would potentially see the imine formation. So when we react the nitrogen, so we go ahead and circle those, the nitrogen with the aldehyde in this case, we would end up with our imine structure. That can then be reduced using the hydrogen and the palladium down to the primary imine. So I would expect the imine to show up because that goes back to the carbonyl chemistry. The rest of those, probably not all that likely. I would guess the Gabriel synthesis isn't going to show up at all. I'd be really surprised if you saw that, even though it is kind of neat. A secondary reason why you might see the reductive amination is that if we wanted to then push through and get a secondary amine or a tertiary amine, we could go through and do that, or subsequent reductive aminations with new alkyl groups to generate those varying levels, primary, secondary, or tertiary. That is pretty much it as far as your synthetic strategies go for making amines. So after that, we could go through and look at the acylation of amines, and this is one that's similar to what we saw already. We're forming that amide bond, and there are aspects of that we've already talked about. We do need 2 moles of the amine because, why? The amine will act as a base and deprotonate an intermediate. That means that if we go through and just put in one equivalent of the amine, one of those equivalents will have to act, or half of that equivalent will have to act as a base, half of that equivalent will have to act as our nucleophile, and we lose that reactivity. We typically don't see the polysubstitution just because once that nitrogen is then attached to that structure, we've neutralized the electrophilicity of that carbonyl carbon. So we don't have to stress about that running another addition reaction. The more important aspect of this whole slide is really looking at it acting as a protecting group. How might it act as a protecting group? Can we remove the carbonyl? Is that a reversible reaction? What happens if I add a bunch of water to this? Break the pi bond, reform the pi bond, kick out our leaving group. So this is a relatively reversible reaction. We can reverse the amide formation. So we could go through and limit the amine's ability to react by putting on an acyl group. We still have that lone pair. Why is that lone pair not willing to act as a base anymore?
Steric hindrance.
Steric hindrance is a big option. There's another big reason.
Resonance.
Yeah. Hopefully you
It's always one of the two,
Yeah.
so.
was suspicious that's what you were saying. What we're looking at is that nitrogen can donate electron density into the carbonyl, and we can get a resonance stabilization of that lone pair. That means it can't act as much as a base, so we lose that base effect with our amines. So that's kind of a nice deal. It also becomes important when we look at the reactivity in EAS reactions. Why would that change our reactivity in EAS reactions? Might help if we shifted to, oh shoot, shouldn't have seen all that. Pretend you can only see part of that. Why, if we're going to put on that bromine, do we not just add bromine to begin with? Why not just add Br2 from the get-go? Why do we have to go through those intermediates? Wouldn't go quite as far as deactivated. If we look at atom X in our amide, atom X still has that lone pair. That can still be donated in. So it's not a deactivated ring, okay, which is a good thing if we wanted the bromine at the para position. Okay, because if it was deactivated, the bromine would go meta. Okay, if we'd done the nitrogen from the get-go, okay, that is extremely activated. The lone pair on that nitrogen can only go into the aromatic ring. Whereas in the case of the amide, where can that lone pair also potentially go? Into our carbonyl structure through resonance. So we lose some of the activity of the amine, which would help us put on only a single bromine. Whereas if we went through and did, I guess we can color code that, our purple pathway with our Br2, that is now a strongly activated structure due to that nitrogen. We would likely see the bromine go in the para position. Okay? How sterically hindered is that ortho? It's a little bit. We've got that lone pair, but there isn't a massive amount of electron density. So we could potentially also see that ortho substitution happen. What makes this further kind of obnoxious as far as the chemistry goes is that that nitrogen is still activating. So not only could we get the mono substitutions, but we could also potentially see two bromines get added to our structure. Okay? Well, if we only want one, and we only want that one at the para position, we need to limit some of that reactivity and prevent the ortho from occurring. The amide functional group can do that quite well. Okay? Does that kind of make sense? So really what we're doing is taking advantage of some of the secondary chemistry of our nitrogen, and then using that to both activate our ring to get that ring to react, but then also limit some of that activity by putting on that acyl group. All right, was there a question, Zena?
It says BR2, not with FeBr3, just BR2.
Good question. So in general, why does it say only BR2 and not the FeBr3? What does FeBr3 act as? It acts as a catalyst. So that turns our standard electrophile now into a really, really, really good electrophile. What happens if we have a really good electrophile? We're going to get a lot more substitutions. Okay. Now we're going to start to see that react as fast as possible with whatever's most quickly and readily available. Okay. So if we want to limit, again, and a lot of what we're looking at within this slide is looking at limiting that reactivity. So what we can do is limit the reactivity of our electrophile by not putting in that catalyst. But then we can also limit the reactivity of the nucleophile by changing that nitrogen. Make sense? It's a good question. What if we went through and did an alkylation? We're going to run through the exact same issue. If you remember all the way back with our alkylation reactions, one of the primary issues that we ran into with those, with the Friedel-Crafts alkylations, is that you tended to get a lot of polyalkylation. In fact, that was one of the test questions, I think, on that section of material. Why does the Friedel-Crafts reagent generate polyalkylation? Well, let's ignore the nitrogen section for a minute. As soon as we put on that CH3, what's the difference now between our starting ring and our end result ring? It's more activated. So with our Friedel-Crafts alkylation, as soon as we put on a single alkyl group, we've now activated our product to react even further. Well, if we only want one alkyl group put on there, we have to limit that chemistry somehow. Okay? And that's something that we could go through and use with our amide. Okay? So we can now kind of limit some of that chemistry. Okay? Again, same kind of idea. We still get that steric blocking with that larger group, preventing that ortho substitution. Okay? Oh, this was an extra one. We can also do some Hofmann eliminations with this. I kind of doubt that you would see this just because you're looking at an awful lot of different substituents and pieces going through on this one. If we start with our amine to begin with, okay, we do have the potential for a leaving group. We could have, oh, this is actually an interesting one. If we were going to try and look at that amine acting as a leaving group, okay, we'd get NH2 minus. How stable is that? is pretty horribly stable. That's a really, really strong base that's not going to work for us. Okay, so if we want to do an elimination where we can kick that leaving group off, we're going to have to minimize its effect or maximize its stability somehow. To do that, what we can do is a secondary or a primary, forget what I was calling it with our alcohols, a pre-activation. Okay, with our alcohols, to get our alcohols to react, we had to add an acid. Okay, that acid then protonated the alcohol, and now we had a good leaving group. We can do something similar in this case, but if we just add acid, that kicks it off as ammonia. Now it's more stable, but what's the issue with our standard ammonias, our NH3s? It's still a good base, and it's still a good nucleophile. Okay, so as soon as we put on that hydrogen, it can kick it off, still have that nucleophile. That's going to be problematic. Okay? So we need to completely mitigate its reactivity altogether. Okay, so we want to kind of sterically hinder it as best as we can. So our pre-activation, instead of putting on hydrogens, will be to put on methyl groups. So we can do a standard substitution reaction where now our nitrogen will act as a nucleophile, kick out the leaving group of our iodide, and because nitrogen is such a good nucleophile and our methyl groups aren't sterically hindering enough, we can turn that into the quaternary salt. Okay, and this is what Josh, you and I were talking about after class on Wednesday, right? The verdict that we came up with is that our methyl groups are too small to really prevent the nitrogen from reacting. Okay, so it will continue to act as a nucleophile. Realize that we have to have that nitrogen act as a nucleophile 3 times. Okay, 2 times to trade out our hydrogens. 3 times. Yeah. And as soon as we make them ethyl groups, we start to lose that nucleophilic ability. Okay? For example, one of the bases, if you remember way back, triethylamine, if we put ethyl groups on there, we said that structure only acted as a base and not as a nucleophile. Whereas if it's a methyl, apparently now it can still act as a nucleophile. The methyl groups don't sterically block it. So it's a kind of an odd situation. And I haven't seen anything better to explain that other than your nitrogens or your methyl groups just aren't big enough. Okay? At that point, we now have a really good leaving group. Okay? Because the nitrogen now can't act as a nucleophile or act as good of a nucleophile in that situation. Okay? Because we now have those methyl groups kind of blocking it out a little bit. We still will now have a bunch of iodide present in solution. And iodide is a relatively good nucleophile, so that could help us out as well if we wanted to do some kind of substitution. The next reagent we add, which definitely looks a little bit odd, and you're not responsible for understanding the mechanism of it, is that silver oxide. Okay? That's kind of neat because in the presence of that iodide ion, silver will react with the iodide to form silver iodide. Go all the way back, 151, 152. Remember your solubility rules? What's the solubility of silver iodide? I know everybody had those memorized, right? Silver iodide is a solid, very, very, very low solubility. Okay? So we can take advantage of that by having the silver pull the iodide ion out of solution. What makes that even better is that in the process of doing that chemistry, we generate hydroxide. Hydroxide is going to be nice because now we have a strong base, whereas before we didn't have as strong of a base. Okay? That, for some reason, facilitates the Hofmann elimination, and the hydrogen we end up removing is the one on the outside. Okay? And it likely has to do with this big, bulky group preventing access to our, go ahead and call it a blue hydrogen. Okay? The free rotation about our single bond is going to prevent those blue hydrogens from getting removed. We're going to get that steric hindrance, and we're really going to do the elimination that forms on the outside. Okay? So we would still have our hydrogens in there. We'd end up with our hydrogen there. Okay? So it's just kind of a neat extra result that you can get out of your amines. You can do a Hofmann elimination by converting the nitrogen into a really good leaving group. Is that a question? Nope. Okay. Questions about that one? We looked at some of these. We can look at the diazonium salts. So we made dyes by forming that exact structure in the middle. Okay. What was special about that species? We do get a little bit of conjugation, but that's not going to be the big important aspect of it. It's a hint. That structure is missing electrons, so it is a pretty good electrophile. Okay. The other thing that's kind of nice about this structure, we didn't take advantage of it when we looked at the dyes, but what do we have very, very close to right there in our purple? Yeah. We take a look at our Lewis structure for nitrogen gas. We are darn close to being able to kick off nitrogen gas. Okay? Which means we have a really, really good leaving group. Okay? So that means that if we can then make our carbon, okay, so now our carbon will be electrophilic. We need to react that with some nucleophile. Okay? So as long as we supply that nucleophile, we can then do this substitution reaction. What kind of mechanism do you think we're approximating here? SN1? SN2? Is there another mechanism? With aromatic rings?
Yeah.
EAS would work if the aromatic ring acted as a nucleophile. So not EAS, but probably NAS. We're looking at the aromatic ring acting as an electrophile with some nucleophile. So we're probably pushing something similar to the NAS mechanism. Okay. If we take a look at our reagent conditions, we're not looking at basic conditions, which means we aren't looking at the elimination addition mechanism. Okay. So with our our aromatic rings, we had the EAS, the NAS, and then elimination addition. Okay. So we're probably looking at something approximating the NAS mechanism, that really good leaving group. Okay. As a side note, did they put it up there? Yeah, they did. These structures are typically seen a lot of times because of that really good nitrogen leaving group. One of the more common methods, looking at alkyl diazonium salts, right? They notice there that they're extremely reactive. Why are they extremely reactive?
Really good leaving group.
You have that really good leaving group. So that, or whatever that atom is, becomes very, very, very positive. If instead of it being an aromatic ring, we made that a carbon, what we're looking at is the diazomethanes. Okay? Really, really interesting chemistry because we now have a methane that is extremely reactive. Okay? The problem with that extremely reactive is that it is so reactive that if while in the process of making the diazomethane you happen to touch the glass, it tends to explode very, very, very violently. To the point where when I was trying to use this kind of reagent, my advisor said, no, you can't use it. Okay, so it is an extremely explosive process. Usually requires someone that has all their hands and doesn't mind losing fingers in the process. Okay, because it is exceptionally difficult to deal with. You also need special glassware. You notice your glassware all has that joint, okay, that kind of powdered glass. The friction in that powdered glass is enough to cause it to combust as well, because that leaving group is just that good. The aromatic ring helps us out a little bit because instead of it now just being a positive on that carbon, I also have the pi system. I have a lot of electron density there that can kind of stabilize the electrophilicity enough that it doesn't get that explosive. Okay, that explosive. Okay, so just kind of a neat thing to consider. So this is one of the reasons why they'll shift the aryl groups for this, because it doesn't blow up on you. So if you wanted to go through and do that substitution reaction, you've got a variety of different options. I resized the figure, but at the same time lost the image. We can put on a variety of different nucleophiles at that position. Okay? So just depending on those systems. You'll notice in all cases they're working with copper. Copper helps to facilitate the breaking of that bond. Okay? That copper can help coordinate the electron density in that range to help kind of slow that reaction a little bit so it doesn't happen quite as explosively. Okay? So kind of cool in that respect. Now we're getting to what we saw in the lab. Everybody is in the lab, so you guys should remember this one. What type of chemistry are we doing in this case? What does it say? Oh man, it says up there. Which type of chemistry were we doing? We're looking at an EAS reaction. We have a really good electrophile in the aryl azo compound. So a nucleophilic ring can go through and attack. Why did it not attack the positive nitrogen? Because typically when we look at an electrophile, what charge does it have? Positive. Why does it not attack the or where our formal positive charge is located? Kind of has to do with resonance. For it to act as an electrophile, what has to happen? We've got to be a little bit careful with it needs to be positive. Because if we take a look at where our nucleophile attacked, that one's not positive. Why does it not attack our positive nitrogen? Our positive nitrogen already has too many electrons. Okay? It can't accept more electrons from outside. It has to take them from within inside. Okay? So if you went back to, hopefully you guys all reviewed it for the lab quiz, that EAS quiz, the very first one that we went through and did, I had you identify acids versus electrophiles. And then you had to identify which atom was the reactive one. Okay? And the common example that I can remember off the top of my head, we looked at this structure. How does this species act? Acts as an acid. Where's our reactive atom? The hydrogen. Interesting. That hydrogen is not positively charged. Why is our reactivity at the hydrogen? The oxygen is electron deficient, sucking the electron density away. Okay? So it's not always the charge, but it is always very, very close to where the charge is, where your chemistry is going to occur. Okay? So we're looking at that EAS reaction, go through all those fun sigma structures, and you can end up with your diazo compound at the end. What was special about the diazo compound? We get lots and lots of conjugation within the pi system. We can take pi electrons, and we could actually put those electrons all the way out on the opposite side. That conjugation then puts the electron, or the energy of the electrons, within the visible spectrum, which means we get colors, which is why we used it for our azo dye lab, because we could then see those colors. Okay? So that was kind of neat when we looked at those. After that, there is a section known as your heterocycles. What does hetero mean as far as organic chemistry is concerned? Homo is actually same. Hetero is different, and it's in reference to usually just oxygen and nitrogen as far as you guys are concerned, but it could be sulfur is a common one. Phosphorus could be thrown in there. And we don't go much beyond that because we're organic chemists and we're lazy. We only deal with the top half of the periodic table, right? Okay. So officially, we could have seen the heterocycles show up when we talked about our oxygen and potentially even our thiol structure as well. Okay. In this case, they decided to bring it in when we're looking at nitrogen. Any idea why nitrogen as a heterocycle is going to become important? And you don't have to look at just the drugs there. Biochemistry, DNA. Okay. We do see nitrogen heterocycles in proteins and amino acids. That's histidine. I actually have that answer. What about adenine? That's in DNA, right? Did I get that one right? Okay. We have a nitrogen heterocycle in that structure as well. That's what's contributing to your hydrogen bonding. Okay. So your nitrogen heterocycles become really, really important as far as biochemistry goes, because that's actually how we put together our DNA. We're looking at the hydrogen bonding effects of those nitrogen heterocycles. Okay. Believe it or not, we've also already looked at these when it comes to pKa's. Okay. So acidity. Why might we expect these substantial acidity differences between pyrrole, pyridine, and cyclohexylamine? Why is pyrrole so much more acidic than cyclohexylamine, or even the pyridine?
The conjugate base is aromatic.
Okay, whenever you're ranking acidity, look at your conjugate bases. The conjugate base of your pyrrole looks like this guy. Why is that important? Throw on that hydrogen. How many pi electrons do we have in that structure? 6 pi electrons in a cyclic structure. We're looking at a compound that is aromatic. What does that do to the stability? Okay, it becomes extremely stable, drops the energy of our structure, which then means the pyrrole really wants to ditch that hydrogen so it can get to that more stable conjugate base. Okay? If you go through and look, or sorry, yeah, I said pyrrole. If we look at pyridine, do we get that same stabilization? Okay, why not?
Did you get 8, I think, pi electrons?
It's kind of a mean question. So there's our lone pair. Structure's already aromatic. Okay? The pi bonds are already in your aromatic situation. Why does our lone pair not contribute to it? Okay, what was that? What was your choice?
sp3 hybridization.
So we can go off of the rules that we were saying in class, that if it's sp3 hybridized, then we can count a lone pair. If it's not sp3 hybridized, you can't count the lone pair. What was
I
your
was just going to
explanation?
say, because the pi bond is already attached to the nitrogen, the lone pair can't be conjugated into the pi system.
Yeah, so you guys are both getting at the same idea. What I was really hoping for was the crazy answer. The lone pair and the pi system are orthogonal to each other, or perpendicular, okay, if we want to get fancy with our words. Okay, so we wouldn't expect to see that nitrogen contribute. Okay, so that would explain why the pyrrole is much more acidic than the pyridine. Why is the pyridine even more acidic than the cyclohexylamine? Because that lone pair is not doing anything fancy. Why is it so much more acidic? If there was resonance stabilization, we would see that electron pair contribute to the pi system. We just said that doesn't happen. Probably Zena's favorite explanation. What's the hybridization difference between our nitrogen and, say, the conjugate base of our cyclohexylamine? So we drew that guy out real quickly. Whoops, I drew it in the ring. We'd have NH2. What's the conjugation of our red nitrogen? sp3 versus our blue nitrogen, sp2. How does that change the structure? sp2 means it's more s character. What's the difference between an s orbital and a p orbital? Shape, and it also has to do with size, which is going to be our our biggest contributing factor. The s orbital is held a little bit closer to the structure than the p orbital. That smaller distance means it's holding the electrons tighter. Is there some word that comes through to explain how an individual atom holds electrons tighter than others? Electronegativity. So the sp2 hybrid atom is more electronegative than the sp3. So why is pyridine more acidic than our cyclohexylamine? Because that nitrogen is more electronegative. Okay? Even though it's the same atom, what we're seeing is that hybridization effect. Okay? That gets in kind of the, oh crap, that's a really hard question kind of section, okay, of the material. Okay? I would not be surprised if you saw something like that on the ACS test. Okay? Hopefully, you would see it in a ranking system with 2 or 3 others, including the pyrrole, and hopefully it wouldn't come down to just comparing between pyridine and the cyclohexylamine. You would hopefully find another answer in there. Okay? Worst case, find the difference. The only real difference that we see between those 2 structures is the hybridization. At that point, you can either keep trying to propagate and say, okay, how does that hybridization effect contribute? It's kind of a nuanced effect. Or you just take a stab at it and guess. Hope for the best. Okay? There are questions on that one? Okay. We can see pyrimidine. That one is the one that I think shows up in adenine. I thought we had a couple biochemists in here. Nobody remember your DNA? Which one of the, I can't even think of the words for them now. The ATCG, which of those has pyrimidine in it? That's a good way to phrase it. It's one of the nitrogenous bases. Good addition. I like that. Okay. So that does show up within DNA. You're also going to be looking at it acting under EAS reactions. Why might we see lower yields with EAS reactions? Is there any other chemistry that could occur?
Because there's more than one nitrogen.
Both pyridine and pyrimidine are going to run into the same issue as far as slow reactions with EAS. Okay, so you're right. The presence of the nitrogen is affecting the reaction. How does the presence of the nitrogen prevent your EAS reaction or slow that rate? In EAS, what does the aromatic ring act as? A nucleophile. What can a nitrogen act as? A nucleophile. If we're going to go through and run an EAS type reaction, we want one of the carbons to react. Those nitrogens might end up reacting instead, okay? Which is going to both reduce yields and probably also mess with the dynamics of the reaction because you're going to shift electron density around within that structure. Okay? So now into the really fun stuff, which is ultimately the end of our chapter. When it comes to spectroscopy and amines, you really don't have a whole lot of tools to grab a hold of. IR is really the only place that I would say is super useful for you guys, and even then it's not all that useful. You do see some broad signals show up in the same range as the alcohol. Why might we expect the same kind of shift as we would for an alcohol? Why is an NH bond similar to an OH bond? Oxygen and nitrogen are both very, very electronegative. They have our second and third highest electronegativities. So we're looking at a very polar bond, pretty much the most polar that we can get. So that is going to put us in that same range. The nitrogen-hydrogen bond tends to be a little bit stronger, okay, which means that the width of the peak gets a little bit narrower. Okay, so the weaker that bond gets, the broader it gets. Think all the way back to the carboxylic acid. What happens to the OH peak in a carboxylic acid? First off, it shifts much lower, and then it gets massively broad and makes it virtually impossible to actually identify peaks because it's so broad. Okay? So your NH peaks tend to be a little bit narrower than your OH, and they also tend to be a little bit weaker. Okay? Depending on the environment, you might see them broad or sharp, so that's kind of a weak one to look at. The biggest aspect that's going to be important for your NH signals in the IR is if you have a primary amine. So our primary amine means we've got a nitrogen attached to one other carbon. How many hydrogens would be attached to that nitrogen then? 2. What we end up seeing for that primary amine is 2 peaks. Okay? We could compare it to saying 1 for each hydrogen. It's officially not the correct answer. It has to do with, again, how we're vibrating those bonds. So IR is all about bond vibration. With 2 hydrogens, oh, it's always fun to do this. You can get symmetric stretching, where they're both going the same general directions, or asymmetric stretching. There we go. those two different stretching modes generate those two peaks. Okay? Because it's still a nitrogen-hydrogen bond that's stretching, that's why you see them in that range. Okay? So if you have a primary amine, look for something in that alcohol range, about 3,300, and look for two peaks. They can be sharp or broad. What happens if it's a secondary amine, though? Well, now one of those hydrogens is another carbon. So now all we'll do is see that one peak. Okay? Again, not as strong as an alcohol, but it could show up. What happens if we take it to tertiary? Now there's no nitrogen, hydrogen. Really, the IR becomes useless for you. The only other signal you could try and pick up would be that carbon to nitrogen bond, which you notice that they don't even mention in there. Why not? Shows up in the fingerprint region, and it shows up very, very similar to the carbon-oxygen bond. So it's very easy to lose track of that. Okay. The last one, still need to check to verify this, but I do not think you'll need mass spec. But the last bit of information that you could pull to get a nitrogen is if you take a look at a mass spec, if you have an odd molecular weight, you have an odd number of nitrogens. Okay, what if you have an even molecular weight? Does that mean there are no nitrogens? No, it just means there's not an odd number. So you could have two nitrogens. Well, if they both contribute an odd molecular weight, what happens? The end result is an even value. Okay? So the last big thing I guess I would say with this, with our mass specs, because I'm pretty sure you guys didn't get to see as much of that as you should have in first semester. If you look at a mass spectrum, it almost always says M to Z at the bottom, M standing for mass, Z standing for charge. All mass spec is looking at a single charge atom. It's always the positive charge. Okay? So when we look at a mass or an M to Z value that says maybe 100, what does that mean? I see a signal there. That means whatever showed up, whatever caused that purple line to be there, has a mass of 100. Okay? So it gives us directly the mass amount. And because we don't have to worry about multiple charges, we don't have to worry about secondary calculations from that. Okay? Yeah, I don't even want to get into intensities with that. The part that I do want to address is that we're saying the molecular ion. So we have to know what the molecular ion is. Okay? Typically is written as the M plus peak. Why plus?
It's a positive charge at that point.
Positive charge. Mass spec is looking at removing an electron. Okay, so the very first thing that happens is we remove an electron, we now have the molecular ion. It will then subsequently decompose into other things. But let's assume our molecular ion is stable enough that it gets detected. That should show up where on our mass spectrum? Okay, it should show up with the largest mass. Why should it be the largest mass? What happens?
Just fragments of it.
Everything else decomposes and falls apart. Okay? So if we look for our signal furthest to the right in mass spec, that should be our molecular ion peak. A couple other things to watch out about. Okay? If we take a look at, what do I want to look at? Hydrogen and carbon. Okay? Does hydrogen always have a molecular weight of 1? No. There are isotopes of hydrogen. Okay? There's isotopes for every single element on here, or on your periodic table, which is why when you look at the molecular weights, you don't typically get exact numbers. They're not exact because we have an average on our periodic table. It's the average molecular weight of all of the isotopes. That means when we go through and take a look at a mass spectrum, we're not looking at probably pure hydrogen or pure carbon or pure any element. We're looking at the standard compilation or the average molecular weight for all of those ions. Mass spec is specific enough that it will detect each and every single value, which means the peak furthest to the right is likely due to an isotope effect of either hydrogen or carbon. So how do you know what the molecular ion peak is then? That isotope effect is usually something in very low concentrations, which means we get a fairly short peak. I noticed I wasn't going to talk about height. So what you can do, take a look at the peak furthest to the right. The tallest peak within 3 units of that peak is your molecular ion, 95% of the time. Okay. The other 5% of the time, you need to have a full lecture on mass spec, and that's not this semester. Okay? So you got other questions with mass spec, you can talk to me after class. And I'm pretty sure that puts us into reviewing everything. Okay, so before we start with that, because I'm sure that will be exciting, do you guys have any questions in general? I know I already did that sort of feel out to see how much work you guys did over the break. Sounded like we're probably just reviewing today.
Amines, where do they fit into this naming of?
Please say it's next slide. Good. Where do amides show up? That's a very good question. I definitely built this on a lower level organic chemistry class, and so I simplified and removed some of the lesser functional groups. Amines are definitely going to be relatively high on this. I will attempt to get a better answer for you, but I'm going to guess they're going to show up.
Before alcohol somewhere probably. And
I would probably put them
over there.
below esters, but above aldehydes and ketones. Because ultimately your aldehyde and an amide is an amine with a ketone. An ester is a ketone with an alcohol. So you're probably looking at something similar in that situation. And the amines are ranked 1 tier below alcohols, so I would put the amides 1 tier below the ester, which is the most similar to it.
That makes sense.
So is there logic behind this? No.
Define logic.
Like, should we think about reactivity? What? It's not even.
I don't think you can really get away with reactivity. Yeah, because your esters are typically your least reactive. Okay, they're very low as far as reactivity. You do have that carbonyl chemistry, but that carbonyl chemistry is stabilized by the oxygen. Okay, so they're put higher than aldehydes and ketones, and their reactivity is definitely lower than them.
Just memorize, basically.
When it comes to nomenclature, and this is why it's my favorite subject, it's really a bunch of old people sat down and said, these are the rules, we are going to follow these rules. They likely had some initial preconceptions on how they would put it together. When it comes to naming for your final, I don't think you're going to see more than these, okay? Which is something that would start to push me to hesitate mentioning amines. Because we had other functional groups. We had anhydrides. We had acyl chlorides or acid chlorides. Which other ones do we run into? We had amines. Okay? You'll notice none of those functional groups are listed up there. And that's because typically when we encounter them, we aren't really trying to name them. What was the question? Not amines, imines. Yeah. Imine. Which is probably a tier below ketones, but above alcohols. Because again, it's similar to your aldehydes and ketones. So you will probably see the functional group names show up. You will not be expected to name them beyond that is this functional group. Okay? The strict nomenclature, how do you name this compound? I would expect everything on this list is absolutely fair game, and you probably won't need amines. Yeah, I mean, as far as strict nomenclature, I think everything on that list is fair game, and I don't think anything that we've talked about this semester. As an extra functional group, you need the strict nomenclature rules on. You should recognize the name of it. So if I say you're dealing with an anhydride, you should be able to, at very least, give me that general structure that we're looking at are anhydride. Okay. A couple of you have gone through a lot of the ACS test booklet. Have you seen nomenclature hit anything other than these? I know you.
Pretty easy, because all you have to do is look at the answer that they
Yeah.
give you, because it really has nothing, it'll tell you what the priority it wants. They're pretty
Okay.
straightforward with that.
So you can pretty much ignore the priorities then. Again, that's why I don't like nomenclature, because it's just a rule that I never bothered to memorize. If I can draw it and show how it reacts, that's good enough. Okay. Find your longest carbon chain. You should remember your metheth, prop-butes, all of those. You could go through and apply these same rules back to all the other functional groups that we've gone through and done with all the different examples. And in most cases, this gets you through those without needing all those specific details. Okay. Did I put on? Yeah, I did. We've got the functional groups. Did I cover? I still need to add functional groups to this because we don't have the acid derivatives. So the acid chlorides and things like that, your anhydrides. You should be familiar with every single one of these functional groups and should have some idea of their reactivity. Okay? You don't necessarily need to name them, but you should look at it and say, oh, I've got an amine, that gives me a nitrogen, that's a good source of electrons, which means it can act as a nucleophile and a base. Or we take a look at the aldehyde and say, oh, an aldehyde means I've got a carbonyl at the end of a carbon chain, okay, which means the reactivity I would expect for that aldehyde. Okay, why is it nucleophilic? Oh, you said electrophile? Okay, why is it electrophilic?
Because the oxygen is withdrawn the electron from carbon, make it partially positive.
So you should be seeing your positive on that carbon. So we have that strong electrophile. And nucleophilic was fine too with that oxygen. Why do we typically not look at the oxygen as being a good electron source? It's pretty much tied up in with that positive carbon, okay, and that it's or highly electronegative. Okay? So we don't expect those other secondary chemistries. What's another issue with carbonyls? Just throw you under the bus from the last test. So our carbonyls give us that good electrophilic carbon, but what else do they do? If you go to the alpha carbon, we've got chemistry with that hydrogen. What's that chemistry? I want a little bit more than acid base. That means it could act as a base too. That can only act as an acid. Okay. If we removed that hydrogen, just to fill out your answer a little bit better, if we removed that hydrogen in an acid-base reaction, then what do we have? We have a nucleophile and a base. Okay? So hopefully at this point, you guys can go through and tackle pretty much any problem based on looking for those chemistries. That's one of the reasons when we went through and talked about each of these functional groups, that here's an electrophile, here's a nucleophile. And yes, that was awfully repetitive, but that's where you should be at. So when you see a new functional group, you can start to predict where that chemistry is located, what it can potentially do. Some of those secondary effects, like we saw in chapter 22 with that alpha carbon, those are just going to be tricky. Ultimately, those were discovered probably by accident. Someone was trying to react the carbonyl carbon and went, whoops, something else happened. Okay. So you should be familiar with all of those and what their chemistry is associated with. Along those lines, just to be mean because I know you all are weak with it, what happens when you see peroxies? I'll accept two chemistries you should be thinking of. What two chemistries? Peroxy, the top one, is not an acid. The oxygen-oxygen bond is exceptionally weak, which pushes two different forms of chemistry that you could deal with.
Can act as a base?
Not very well. Both of those are going to be pretty acidic. The peroxy, if that bond, can you see that? Projector's not the greatest. shift that a little bit. Stop. Okay, if we take a look at that bond, if it's really, really weak, okay, it's really, really weak because why? They're both very electronegative. Which one's more electronegative? They're equal, which means they both will equally pull their electron out, which means we have what mechanism? You've got radical formation. So if you see a peroxy, you should be thinking radicals as a potential chemistry. Okay? Even with the peroxy acid, I would still push radicals as a thought process. The peroxy acid really introduces an extra piece of chemistry.
The carbonyl chemistry.
No, you get the Beer-Villiger. Is that what you're thinking about with carbonyl chemistry? Or are you talking about the carbonyl within this structure? Yeah. That carbonyl is going to cause that bond to polarize a little bit better. All right, than with our standard peroxy. Okay. Which means this oxygen acts very well as, should it be a nucleophile? It should act as an electrophile because it just lost electrons due to that carbonyl. So actually a good call. That carbonyl is going to help polarize that bond. And now we have that oxygen-oxygen bond, but it is now very polarized to one side or the other. So we get a relatively electrophilic oxygen. How often do we get an electrophilic oxygen? Okay, not very often. I think this is probably the only place that we get that electrophilic oxygen. Okay, because we just can't get something more electronegative than it to help polarize it. All right. You saw that with, we've already mentioned where I thought you were going with that, the Beer-Villiger reaction, reacting with our peroxy acids with ketones. Okay, we could then insert that electrophilic oxygen into that bond, and we ended up with an ester. Vaguely remember? Okay, kind of, sort of. The other common place is, maybe if I gave you the initials. MCPBA. Stand for metachloroperoxybenzoic acid. You got the right functional group, but the wrong action. MCPBA gave you the epoxide. Okay. We can react an alkene with MCPBA to make the epoxide. Okay. Which brings us back to alkenes. What would we expect alkenes to react as? Which is it? Why should it act as a nucleophile? We have that pi bond, which is our source of pi electrons. Those pi electrons will then push out for it acting as a nucleophile. Okay. Okay. So get an idea, go through and pick a few of them and just say, okay, what chemistry can I do with any one of these? I did want to include this because we did run into a couple issues with the aromatic common names. So I wanted to make sure this was part of your slides. I would guess toluene, phenol, and aniline are going to be your really common ones that are going to show up on the ACS test, so you'll have to know those. The other ones, to a much lesser extent, you should know those. So you got toluene, phenol, and aniline. I would guess if one of those other ones showed up, you would be given the structure. Okay? I'd be surprised if those show up directly on their own. Okay? If we went back to the aromatic ring here, because we got so used to referring to everything as our ortho, meta, and para positions, and as we talked about last week, our ortho, meta, and para do not show up. We need to know the correct nomenclature system, which is using IUPAC. How do we refer to the ortho positions? Where does our numbering start? At our X, which will be our highest priority. So there's 1, 2, 3, 4, 5, and 6. Our ortho positions are 2 and 6. Okay. Where's our meta position? 3 and 5, and our para at position 4. Okay? So it really does sound like you will only be seeing the numbered positions. So work with and make sure you know where those numbered positions are. Yeah?
Just a quick question. I can't find an answer to it. Percentage-wise, what are we looking at in terms of each section? Because I know that the exam is broken into the sections.
No, it's not. The exam is completely shuffled. There, you will see nomenclature questions both at the beginning and at the end. I would say it does kind of trend more towards first semester stuff and progress more towards second semester stuff. The very last questions of the exam are all strictly spectroscopy, but everything else is kind of shuffled around between sections. So you're not going to get the organization that you would hope that you've been seeing on the in-class exams. I always go back and forth on that. There's usually enough of an uproar from students that I keep it locked in. Okay? So more so than ever, when you take the test, jump through it. Find the answers that ring out true to you, answer those first, and then double back through and find the more difficult ones. Okay? Going in sequence will probably hurt you. Okay? Check page 1 first and kind of simplify through it. Okay? Because they do some kind of beginning towards end transition. It's just not very clear. Okay? And then as far as exact breakdowns go, they don't give it out. I won't give it out. Okay? I will be going through and doing that, but I'm not going to give it out. Okay? Bonds, forces, and effects. Okay? Really big in first semester and ultimately in lab dealing with this kind of a slide. We're looking at the interplay between the bonds and forces. Ultimately, all chemistry is looking at the interaction between any two atoms. If we start bringing those two atoms near each other, we would start seeing a London dispersion force, okay, as an attraction between them. Let's go red. If they continue to get brought closer to each other and satisfy further requirements, we could start getting a dipole-dipole force or hydrogen bonding or an ionic force. Ionic forces tend to pick up that kind of weird transition because they can both be a force, and if we push it even further along as far as the interaction between those atoms, we can turn it into an ionic bond. If we continue to strengthen that interaction, we can push through polar covalent and into covalent bonds. So we're looking at a start and an end as far as strength of the attractive force between them. All right, there are definitely many places where this gets confused. These are two separate topics. One is an intermolecular force, one is an intramolecular bond. Okay? So what we're concerned about with organic chemistry is when does the force become a bond? So when we're looking at substitution, we can have a nucleophile come in and interact strongly with our partial positive electrophile until eventually that attractive force gets so great that it starts to become a bond and we kick off our leaving group. So what we're looking at in all cases is somewhere in this start and pushing somewhere around towards the end to see what happens. Typically we don't end in the covalent situation. Why? To get that covalent bond, we had to have equal sharing of electrons. Ultimately, as far as we're concerned, that is carbon and hydrogen. Maybe easy to get a positive hydrogen. How easy is it to get a negative carbon? Okay. Relatively not easy. So most situations, we don't end in that covalent area, we end in that polar covalent area. This can come helpful the other direction. If you have a polar covalent bond, that means you've generated these dipoles. Those dipoles you can take advantage of. That's where we're finding our positives and our negative. And we ultimately put them together to generate a new polar covalent bond. Okay? Where this becomes super important as far as ACS questions go would be melting points, boiling points, even solubility. Okay? When we're looking at melting points or boiling points, physically what is happening? You are breaking and forming, this is where it gets tricky, forces, not bonds. So if we took a look at the compound water versus methane, which one would we expect to have the higher melting point or boiling point? H2O, because we get hydrogen bonding in the water. Okay? Where I think this becomes exceedingly dangerous is if we then go through and compared something like this. And now we're trying to figure out what is happening. Well, what's the interaction that we have between sodium and chloride? Ionic bond, not a force. So when we look at sodium chloride, yes, we see a solid, but that's because to melt that, we have to break the bonds. To melt water, what do we have to break? The forces. Okay? So it's where we slide on that ionic interaction. Are we pushing something that is a solid, or are we push or force versus bond? It's that kind of balance back and forth that makes, in my opinion, it difficult to determine what's happening with those. Okay? Realize that our covalent bond is always stronger than our ionic bond. Okay? To break the bond in H2O, it will very likely take more energy than it will to break the bond in sodium chloride. Okay? But we rarely ever do that. Okay? Solubility. What's our rule when it comes to solubility? Like dissolves like. Let's make that a little bit more useful. It's not just like dissolves like. It's like what dissolves like what. Like forces dissolve like forces. So you could go through, if we wanted to figure out what compounds are going to dissolve in water. Well, water's hydrogen bonding. Take a look at that other compound. Does it have hydrogen bonding? If so, those are likely soluble. If we're looking at multiple compounds, let's go with CH2, CH2, OH versus ethanol, which I'm going to have to drop all the way to the bottom, CH3, CH2, OH. Which one would we predict to be more soluble in water? Top or bottom? Top, because more like forces. Okay? So it's still always that like dissolves like. As far as your ACS test goes, they will be very straightforward and simple. Any of you that took solubility labs in first semester, it's not always straightforward and simple. Those don't show up on your final test. Okay? Those would be more a lab situation trying to get you to evaluate and see that solubility is not as simple as like dissolves like. Yeah?
So is that where salts dissociating in water?
So if we take a look at trying to dissolve a salt into water, which is another tricky one. Okay? Sodium chloride, that's a relatively strong bond. We'd be replacing that with a hydrogen bond. Okay? Ionic versus hydrogen bonding. Ionic is much stronger. Our initial prediction is that we do not see salt dissolve in water. Okay? But it does. So how can we explain that it does? Is it only one hydrogen bonding interaction? No, it's the sum force of 4 or 5 hydrogen bonding interactions. Okay, and that's really what makes salts even more complicated, is that when we dissolve salts in water, we're getting that stacking effect of multiple weaker, but also still strong hydrogen bonding interactions. Okay, does that answer your question well enough?
Yeah, so I mean, that would just be one of those.
It's kind of it's more a special case. And I wouldn't quite go as far as calling it as an exception, but it's, yeah, a kind of weird gray area. Okay. Everything that I've seen has been along the lines of hydrogen bonding. Okay. Here's water, what dissolves in it? Does it have hydrogen bonding? How many hydrogen bonding effects does it have? Okay. Other questions on this one? Must be Monday. After a holiday, even better. Okay. The other big thing, I did mean to go back through and add one extra section on this, but we will talk about it later on. Know your reactions. Your acid-base, substitution, elimination, addition. Everything we've done this semester is some multiplication thereof. Okay? We did an acid-base reaction followed by a substitution. We did a substitution reaction followed by an addition, or an addition followed by an elimination. So if you can identify the different types of things that are happening within an individual reaction, or what need to happen, that can allow you to start to predict what reagents to go through and use. Otherwise, you absolutely have to have it 100% strictly memorized and good luck. Okay? So given a new reaction, identify your changes. Identify the bonds broken, identify the bonds formed, and say, how can I do that? How can I break a pi bond? All right, it's a good question. How can you break a pi bond? What would you need? You need an electrophile, or, what was that? You say resonance?
I changed my mind.
Oh, okay. So an electrophile is positive. Why do you need something positive?
Because it's electron density.
The pi bond has electrons, right? So we need something positive. A good something positive is an electrophile. What's another thing that's positive that we don't call an electrophile? Acids, H+. Okay? So if I have a pi bond and I know that needs to break, hydrogen is a really good option, probably one of your most common ones. Okay? Biggest reason why it's going to show up a lot is that when they then draw the product, do they show the hydrogen? No. So it requires an extra layer of interpretation on your part to make sure that you see that difference and identify that change. Okay? So make sure that you can identify them, hopefully at site. So at site, last one on this, what do we have? We've got an addition. What are our characteristics that mean it was an addition? Okay, so you could say we're starting with two things. Something about a pi bond. What happened to the pi bond?
Your pi bond's broken in the product.
Lost the pi bond. I would probably trigger on the loss of the pi bond because in a lot of these cases, we start with two things. Okay, so the loss of the pi bond to me is the easier thing to see. Okay, but you're absolutely right. If we start with two things, that does help us. What does that do? That eliminates the option of looking at the elimination reaction. Can't possibly be in our elimination. So what do we expect to see in our elimination reaction?
Pi bond formed.
We would expect to see a pi formed. So it's trying to zero in on those big changes. What happens in the next one up? We're seeing a substitution. Okay? One of the more common things that I've seen, almost always when you take a look at a substitution reaction, you guys are probably used to this. We see a substrate and we see a nucleophile. Where's the nucleophile almost always get written? It's usually on top of the arrow. What's a really easy way to confuse students? Swap them. Yeah, put the solvent. Instead of putting the nucleophile on the arrow, put the substrate on the arrow. Okay? Go back to the amines that we just looked at. Okay? Our substrate, when we looked at the amines and trying to make that Hofmann elimination slide, okay, where was the substrate? It was over the arrow. Okay? And now, because we've swapped the location of where we're used to seeing that, we tend to go, oh my gosh, it's a brand new thing. It's still a substitution reaction. So identify the pieces as best as you can. Okay? The other thing that can be obnoxious is if we do put the nucleophile on top of the arrow, now we start to say, oh, there's only one thing reacting. Okay? And then that can shift our focus around, make it look like an elimination. So try and look for those big changes. Look for the pieces that have shifted locations. The very top one, process of elimination, acid and base. The acid-base ones can be a little bit trickier, typically because we can run acid-base reactions at the same time that we're doing something else, which I think is where you're going with that. But if it is strictly an acid-base reaction, it must involve hydrogens. What happens when we put the hydrogen on the product? Do we have to show it? Depending on what we're putting it on, it may not show up. Okay? So it may look like, oh, you've all of a sudden lost reactivity. Oh, what the heck happened? You probably put on a hydrogen. Okay, so again, try and look for those pieces and try and identify them as best you can. Okay? Big definitions. Okay? I don't think I've made as big a deal as I should have this semester about going over these. Hopefully you guys disagree with that statement, but I won't make you tell me I'm wrong. Okay? I identifying and knowing these definitions is important, because if you know you have a Bronsted acid, what does it need to react with? Bronsted base. So if you can come up with and look at those overall reaction pieces and start to identify what reactions are happening, you can start to also apply what things do I need to show up in it. Okay? So for elimination reactions, we did do the formation of a pi bond. What else happened in the process of forming our pi bond? There's an H plus floating around, which means our starting material had to act as an acid. It donated a hydrogen out into the solution. What could facilitate that reaction? What could help remove a hydrogen? A base. Okay? So knowing those definitions is really important. Should I go through and write those definitions in, or you guys think you got them? Okay, we're writing them in. Bronsted acid, definition. Proton donor, also known as our H+, or a dower. Bronsted base, we're looking at a proton acceptor. Lewis base, electron donor. Okay. The base definition never changes. A Bronsted base has to accept hydrogens, which means what does it need to give up? Electrons. So if we're looking at a Lewis base, as soon as we switch to Lewis, we're now looking at the flow of electrons. Did it donate or accept electrons? Well, if we've got the Bronsted down, it has to be an electron donor. Okay, our Lewis acid, we've got an electron acceptor. Our electrophile, an electron acceptor, and our nucleophile, an electron donor. So it's not just knowing the definitions, but how do you apply them in each new situation. And that does require a little bit of effort, but if you don't have the definitions nailed down, you can't apply those definitions. Okay? Your acid-base chemistry. This was an attempt at summarizing it as best I could real quickly. When we're looking at hydrogens bound to our halogens, they can only act as acids. We don't really have a choice. When we shift one row further over, or further to the left, we run into our oxygen column. Oxygen falls in this gray area. It can act as both an acid and as a base. We move one row further over onto our nitrogen. We really only see that acting as a base. And we move one step further over, we run into the carbon column, and those will almost always be neutral. Very difficult to get them to act as acids or bases. What's changing as we shift across those? Yeah, it's the electronegativity of those individual atoms. Carbon, being the least electronegative, shares its electrons very well with the hydrogen. We don't see that bond being easily broken. Whereas our halogens tend to have the highest electronegativity. Right? There's other things messing with those as well, which makes them pull the electron density away from the hydrogen a lot, preventing or allowing that bond to break much easier, and we get that acid. Okay? So if you can remember within those columns what's happening. So if I asked you for the reactivity of phosphorus, what would we expect phosphorus to act as? It's probably a base. So that's pulling all the way back from 151 stuff. Within our column, we get very similar chemistry. Okay? That can help us approach these things. How do we alter our acids and base strength? Okay? Kind of comes from your own individual perspective on which you want to work with. I personally, when I want to look at ranking acid strength, I will draw out the conjugate base for every single one of those structures, which can be a bit tedious, but it works. And then I will evaluate the electron density. Now that I have electrons to look at, where can those electrons go? If it's a strong acid, where do the electrons go? They have to go into the structure. If it's a strong acid, if the electrons go to the proton, now we're forming a much stronger bond. We can't break that bond. If the bond never breaks, it can't be an acid. Okay? well, that's pretty darn close. So when you go through and evaluate your acids and base strengths, look for those different patterns. For me, it's all about the electrons. Find the electrons, whichever way you got to go through, and start to evaluate their stability. Okay? The more stable the electrons, okay, in a conjugate base, that means the stronger the acid. The more stable the electrons in a base, the weaker the base. Okay? So always make sure you cross-reference what you were being asked to analyze. Okay? And we'll go ahead and end it there and pick up